Hi everybody, we are picking up from where we left off, which was modeling exponential relations using equations. Very quick lesson here just to finish off the content for the unit. We're going to work with two specific types of exponential relations. And those two specific scenarios is going to be one for Halflife and one for doubling time. Make sure you know how to use these. You don't even have to memorize them, just be familiar with them, because obviously your test and your CCA are going to be open book, so you can just refer to these formulas. But you still have to know how to use them, so this is still important. So we have two specific ones we're going to look at. One for Half-Life and one for doubling time. We're going to set them up very, very similar to how our other general exponential relations were set up. So A equals P. Now, what comes to mind when you think of Half-Life? Half, the word half. Well, 1/2. And we know we have to, for anything exponential, you have to have letters, variables, in your exponent. And your exponent is actually a fraction. So t over h. Now those variables are all the same, like we did a and p in the previous lesson. So remember, a stands for final amount, p starts for the starting amount or initial amount. 1/2 obviously is just 1/2. So, and then t was time. So all those things were the same as what they were before. The only new variable, so I'm not going to write what a, p, and t stand for. I just verbally told you, plus you could refer to the last lesson. But h is a new letter. And h just stands for the half-life. And it'll be quoted to you in the question. Now, if you don't like fractions, I'm going to write an or here. We could rewrite this, and if you don't like fractions, that means you probably like decimals. We could rewrite that as that. So if you like that, you can use 0.5 instead of 1/2. Makes it easier for you. The other type of specific exponential equation we're going to look at, doubling time. A equals P. And then what comes to mind when you see doubling time? So the word double. Hopefully you're thinking 2. If it doubles, it multiplies by 2. Exponent t over d. All those letters are the same. So A, again, final amount, P, starting amount, 2 is just the number 2, T for time, and D for doubling time, which again will be quoted to you in the question. As just an extension of this, if you said tripling time, what would be there instead of the 2? Hopefully you're thinking 3. If I said quadrupling time, hopefully you would say instead of the 2, the 4 would be there. So the general format, the setup of these equations is all the same. The only thing that changes is the base and sometimes the exponent. So keep those two equations in front of you as we just do a couple of quick examples. Our first example, a bacterial culture on your countertop began with 7,500 bacteria and doubles every 30 minutes. Write a formula to model this. So final amount, A equals, the starting amount tells us 7,500. And since it tells you that it doubles, right, you're looking for one of two key words, either half-life or doubles. We know that we're using the doubling time. And then T over D. And D is the doubling time, which it says this right here. This is our doubling time, 30 minutes. So T over 30. What is the population after 30 minutes? All you do is put 30 in for your time. So A equals 7,500, and then put 30 over 30. Now this is important, so I'm going to make a note of this. Make sure you do the exponent calculation first. So you do 30 divided by 30 first, which is 1. So we have A equals 7,500, and then to the power of 1, because 30 divided by 30 is 1. Now type that into your calculator just like you see it. So 7,500, bracket 2, bracket exponent 1. Hopefully you get 15,000. And hopefully that makes sense, even just from a common sense standpoint. And the reason why that makes sense from a common sense standpoint is if I didn't even give you that equation, if I tell you that something doubles every 30 minutes, and I tell you what's the population 30 minutes later, well, if it doubles every 30 minutes, and I'm asking you 30 minutes in the future, that means it's doubled once. What's double 7,500? 15,000. What is the population after 1 hour? So our equation. Now here's where there might be a common mistake. If you're thinking 1 over 30 as your exponent, I like where your head's at, except, because you're knowing that you got to sub in time, except for that exponent has to be the same units. And if you do 1 over 30, you're mixing hours with minutes. So let's convert our hours to minutes to match our doubling time. How many minutes are there in 1 hour? Hopefully you're thinking 60 minutes. So now we're going to do 60 over 30. And remember, do the exponent calculation first. So do 60 divided by 30 first, which is 2. And then enter that into your calculator just like you see it. 7,500, bracket 2, close bracket, and then to the exponent 2. And you should get 30,000. And again, hopefully that makes sense because we know every 30 minutes it doubles, so it's doubled twice in 1 hour. And we just got 15,000, so if we double it another time, we're going to get 30,000. What is the population after 5 hours? So, again, you might be tempted to put 5 over 30, but now you're mixing. You're mixing units. So how many minutes are there in an hour? We just said 60. So do 60 times 5. That's going to give you 300 minutes. So do 300 over 30. Do your exponent calculation first. 300 divided by 30 gives you 10. So 7,500 and then 2 to the power of 10. Enter it just like you see it, brackets and all. And we should get 7,680,000 bacteria. The final part of this, E, it's kind of going the other way. How long does it take for there to be 30,720,000 bacteria? So you got to do trial and error for this. So you're literally just typing into your calculator right now, 7,500 to the 2 in brackets to the exponent. Now, you already know that 2 to the 10, right? You already know 2 to the 10 already gives you 7 million. So we should be picking a number bigger than 10. So let's try 11. Didn't get it. Keep going, pause the video, see if you can figure out what it is. So if you did get the final answer, let's double check. Hopefully you got 12 as your exponent. Now that doesn't mean 12 hours. So we kind of got to do some thinking here. So we know that, okay, so if we got 12, we know that t over 30 has got to equal 12. And that's just a simple cross multiplication. So t equals 30 times 12, which you get 360 minutes. So your answer could be it takes 360 minutes to get that many bacteria, or if we want to make it hours, you could divide by 60. So if we divide that by 60 minutes, we should get 6. So this is an or because you don't have to do this. 6 hours. So hopefully that makes sense. Again, I didn't do any therefore statements, but I'm going to write it like I did for the last lesson. Don't forget to do therefore statements on a test or an exam. And last example, carbon-14 is radioactive. It exists in all living organisms. As an aside, if you're not sure, this is how they roughly date fossils by the amount of carbon-14. Anyway, it has a half-life of about 5,730 years. Write a formula to model this. So you're looking for doubling or half-life. We see half-life. So A equals, now I didn't give you the starting amount yet, so we're just going to put a P there as a placeholder. Half-life, since most of you probably prefer decimals, I'm going to write 0.5. And then it's T over H, which I gave you the half-life, it's right there, 5,730. If there's 26 pounds of carbon in a 200-pound human, how much is left after 5,730 years? After your death. So if you were a fossil. So A equals, now I've given you the starting amount, 26, 0.5, and then I give you the time, right? I said that much time has passed since your tragic death. And remember, do the exponent first, just like for the doubling time. So that divided by that is just 1. So you get 26, 0.5 to the 1. And if you enter that into your calculator, just like you see it, you should get 13 pounds. Just like the previous example, that should make sense from a common sense standpoint. If it halves, right, half-life just means something is cut in half. If it's cut in half every 5,730 years, and that's how much time has passed, it's been cut in half once. What's half of 26? 13. How much is left 50,000 years after your death? And we're still going to assume that it's a 200-pound human. So 0.5, and now it's 50,000 divided by 5,730. Make sure you do the exponent first. So 50,000 divided by 5,730. And you're going to notice here you do not get a very nice number. So let's just say we're going to round to, we'll say 3 decimal places. So 8.726. And then enter that into your calculator. 26, 0.5 in brackets into the exponent 8.726. And what do we get? We get 0.06, I'll go one more decimal place, 1 pounds. So that means even 50,000 years after your death, there's still 0.061 pounds of carbon-14 left. And just like before, do not forget for a test for word problems or a CCA, therefore statements. So that's it for this lesson. Like I said, very quick. You got some workbook questions to work on. And then if you have already completed that and you're working a little bit ahead, there are 2 video review lessons I'm going to do before lunch. Then you'll have lunch and your test. Since there's no assignment for this unit, We just kind of went through it relatively quickly over the course of a day and a half, let's say. So your test is in the afternoon, do not forget. Now, for the Teams drop-in, normally I have it set up for 2 hours, an hour before lunch and an hour after lunch. If you are someone that thinks you're going to use that, just keep in mind I'm going to have an hour open before lunch for you to drop into, and then I will have it open again for an hour during the first hour of the test. So just to reiterate that, if you need help, like live help on Teams, not just email or Asia, I will be in Teams, which remember you can click on it in the activity feed. I will be in a Teams chat waiting for you to get help if you want to drop in from roughly 10:50 to 11:50, and then again from 1 until 2 during your test if you happen to need a little bit of help or clarification during your test. All right, that's it. Talk to you during the review lessons.